My name is Fritz Kagerer. I studied in my bachelor biomathematics and biophysics, and then I made the transition to actually go more into the biological clinical studies and went into to Munich to do the Masters in Biomedical Neurosciences. Yeah, so in my case, my project that I mainly tackle during my PhD is a project in spinal-cord-injury. So this is the model that we use. So we actually produce a spinal-cord injury in the mice, and the idea is that it should kind of mimic something like a traumatic injury of the spinal cord, like for example a car accident, and you actually get a bump on your back, and then you have some damage to your spinal cord. And what happens then is that in our model, the mice can't use their hind legs super well anymore, so they really have troubles to keep their hips in place and actually walk properly. And we can do tests on that to see how the animals recover over time. And what you see is that after some weeks and days, they actually recover fine. So when they walk over a ladder, for example, in the beginning they really can't manage to do it, and then 1 week later they already can walk over it way better. So this is the test that we do. And what was found by our boss was that in rats there was this finding that you have the neurons that come from the corticospinal tract, like they come from the brain down towards your hind legs. This is the regular way how they are actually relayed. But in our case, when we do this injury, this tract is completely capped. Like it can't actually go to the hind legs anymore. And what Florence found, she found that there's actually some collaterals forming, like from these neurons that come from the brain that are actually cut. There's some little arms forming from these neurons, and then they reconnect to other neurons. And in that way, they kind of form a bridge around the lesion. So you have this lesion in your back, and then you have this bridge forming. And with this bridge, it happens that the mice can walk again over this ladder, for example. And so far, most of the work in the lab was on the first formation phase of this bridge building, basically. And now my project is more on the later phases of the refinement, because I compare it, you can compare it a bit to in babies' brains. You have plenty of synapses in the beginning, and then after time, the body realizes, okay, these synapses I don't really need, so it really prunes down most of the synapses, and only the ones that are really functional and needed, they stay. And we believe that in this bridge formation, it's the same thing. There's a lot of connections forming in the beginning, and then out of all these connections, only the ones that are really functional for the hind leg movement are the ones that actually staying and are important. And this is my main project, and what I look at it in this project is neuronal activity of some of the neurons. So actually shut off or activate some of the neurons actively using a chemogenetics, and by that I see how this refinement, like this later phase in the bridge building, is actually working.